Hello students, welcome to Diksha Karnataka YouTube channel. In this video, I am going to discuss the top 30 questions in electromagnetic induction, that is EMI. Okay, so in KCET, if you analyze the KCET previous year question papers, you will see minimum 3 to 4 questions they will ask, okay, from this chapter. So they will ask the same kind of these kind of questions only. Okay, I'm going to solve 30 questions. They will ask, most of the time they will ask these kind of questions only. Okay, so if you are able to solve these questions, so definitely in the exam you will be able to counter these kind of questions. Okay, yeah, let us start. Question number 1. The coil current in a coil changes from 2 ampere to 5 ampere in 0.3 second. The magnitude of EMF induced in the coil is 1 volt, that is E equal to 1 volt. Okay, the value of self-inductance of the coil. So we know the relationship between self-inductance, current and magnetic flux, right? So what is the relationship? The relationship between self-inductance, current and magnetic flux is L into I equal to N into phi, right? L into I equal to N into phi. Now differentiate both sides with respect to T. Now N into d phi by dt is equal to L into di by dt. So what is d phi by dt? Rate of change of magnetic flux. N into d phi by dt is rate of change of magnetic flux, right? So which is equal to EMF, induced EMF E, right? Magnitude of the induced EMF E, which is equal to L into rate of change of current, or you can say change in current over change in time, right? So here E equal to 1 volt, right? So 1 equal to L we need to find, right? L into di, that is change in current. Change in current is final current minus initial current, right? So final current is 5 ampere, right? Initial current is 2 ampere. 5 minus 2 divided by change in time is 0.3. Now L equal to 0.3 into 1 volt divided by 5 minus 2, that is 3. Now solve this, you will get L equal to 100 millihenry. 100 millihenry. So the correct option is A. Question number 2. A metallic rod of length 1 meter held along east-west direction is allowed to fall down freely. Let us draw the rod diagram. This is the rod, metallic rod. Okay, so it is allowed to fall freely, and it is held along east-west direction. Okay, east-west direction. Given horizontal component of Earth's magnetic field BH equal to 3 into 10 to the power minus 5 Tesla. So this is the horizontal component of the Earth's magnetic field. So the direction is from geographic south to north. Okay. The EMF induced in the rod at an instant t equal to 2 seconds after it is released is, that is initial velocity of the rod is 0. Okay. So we need to find the induced EMF produced in the rod after time t equal to 2 seconds, sorry, at an instant t equal to 2 seconds after the rod is released, right? Okay, so how to solve this one, right? So we know that induced EMF E equal to B into V into L, B into V into L sin theta. Theta is angle between V and B. Okay, B into V into L sin theta. Theta is angle between B and B. So this is the velocity of the rod at time t equal to 2 seconds. Okay, what is the direction of the B? So it is from geographic south to north, right? That is perpendicular to the motion of the rod, right? Perpendicular to the motion of the rod. So the angle between B and V is 90 degree, right? So sin 90 degree is 1. So E equal to B into V into L, right? E equal to B into V into L. Now what is the value of V, right? So V is equal to U plus G into T, right? U plus G into T. U equal to 0, right? V equal to G into T. Now substitute expression of V to this equation, E equal to B into G into T into L. Now we know the value of B, G, T, L, right? Substitute. the value of B is 3 into 10 to the power minus 5 Tesla, into G is 10, into T is 2 seconds, right, into L is 1 meter. Now E equal to, solve this, you will get 6 into 10 to the power minus 4 volt. So the correct option is D. Okay, yeah. Next question, question number 3. A square loop of side 2 cm enters a magnetic field with the constant speed of 2 cm per second as shown. The front edge enters the field at t equal to 0 second. Which of the following graph correctly depicts the induced EMF in the loop? Okay, we need to choose the correct graph, right, of E versus T, right? So, okay, let's see. Here, this is the square loop, right? So at time t equal to t, okay, at time t, here some portion of this loop inside the magnetic field region, right? So what is the length? This length will be v into t, right? And this is the velocity v, right? So this length is L, right? So what is the area of this square loop, or area of this portion, right? Area of the portion is A equal to L into V into T, right? So let us find induced EMF produced in this coil, right? So as the coil enters into this magnetic field region, so what happens? Magnetic flux through this coil increases, right? Isn't it? So because of that, induced EMF will be produced, right? So induced EMF will be produced in the coil in such a way that it opposes the increase in magnetic field, right? Okay, so induced EMF in the coil E equal to minus d phi divided by dt, that is rate of change of magnetic flux. Why it is negative sign? Negative sign indicates induced EMF is in the opposite direction, right? Okay, so what is phi? Phi is magnetic flux, right? That is B dot A, right? So in scalar it is BA cos theta. Theta is angle between magnetic field vector and area vector. Both are in the same direction, right? Area vector and magnetic field vector both are in the same direction. So it is B into A, right? So E equal to minus D into BA by dt, right? So here what is changing? The magnetic field is not changing, right? Here the area is changing. Area entering into this magnetic field region is changing, right? Okay, so now I can write E equal to minus B into D into area is L into V into T, right, divided by dt. So now what is the differentiation of T with respect to T? 1, right? So induced EMF E equal to minus BVL, right? So induced EMF E equal to B is here. What is the magnetic field? 0.5 Tesla. So minus of 0.5 into V. V is 2 centimeter per second, right? And what is the square loop here? This area of side of the square loop. So that is 2 centimeter, right? So 2 centimeter per second, that is 2 into 10 to the power minus 2 meter per second into L. L is 2 centimeter, that is 2 into 10 to the power minus 2, right? Now E equal to, here 2 into 0.5 is 1, right? So 1 into 2 is 2. So 2 minus 2, okay, minus 2 into 10 to the power minus 4 volt, right? So induced EMF in this coil is minus 2 into 10 to the power minus 4 volt. So if I draw the graph, E versus T graph, induced EMF produced in the coil is minus 2 into 10 to the power minus 4 volt, right? Isn't it? When the whole square loop enters into this region, that is magnetic field region, there will be no induced EMF, right? There will be no induced EMF in this coil, right? Why? Because the magnetic field is constant, right? Isn't it? Magnetic field is not changing. Here area is also not changing, right? Magnetic field is constant and area is also constant. Area in this area in this region is also constant. It is not changing, right? So therefore induced EMF will be 0, right? Induced EMF produced in this coil is 0. So when the square loop exists exit from this region, okay, when the square loop exit from this region, again induced EMF will be produced, right? So because area is changing, magnetic flux through this loop is decreasing, right? So induced EMF is the same, 2 into 10 to the power minus 4 volt, but the sign is different. So here it will be positive, right? Isn't it? So it will be positive like this. Okay, so this is the graph, E versus T graph. Okay, so the correct option is C. Okay, the correct option is C. Next question, question number 4. A long solenoid has 500 turns when a current of 2 ampere is passed through it. The resulting magnetic flux linked with each turn of the solenoid is 4 into 10 to the power minus 3 Weber. Then self-inductance of the solenoid is, okay, we need to find the value of L, right? We know the relationship between Li and phi, that is magnetic flux. L is self-inductance, I is current in the coil, right? And phi is magnetic flux. So what is the relationship between Li and phi? So L into I equal to N into phi. N is number of turns. Okay. So phi is given, N is given, I is given. We need to find L, right? So L equal to N phi by I. L equal to N is here 500. Phi is here, what is the value of phi? 4 into 10 to the power minus 3 divided by I, 2. So 2 2s are 4. So L equal to 500 into 2, 1000. 1000 into 10 to the power minus 3 is 1. So 1 Henry. So the correct option is C. Okay. Yeah. Next question. Question number 5. A magnetic field of flux density 1 Weber per meter square, that is B, the value of B. Okay. Value of B is 1 Weber per meter square, acts normal to an 80 turn coil of 0.01 meter square area. If the coil is removed from the field in 0.2 second, the EMF induced in it is, okay, when the coil is at the magnetic field, right, magnetic field region, the induced EMF is 0. So when you start removing from this when you start removing the coil from the magnetic field, what happens? Induced EMF will be produced, right? Induced EMF will be produced, that is the magnetic flux through the coil decreases, right? So induced EMF will be produced. So induced EMF here E equal to N into d phi by dt, right? N into d phi by dt, isn't it? N is number of turns, right? Here phi is magnetic flux, isn't it? Phi is magnetic flux. So it is minus N into d phi by dt, okay? Minus N into d phi by dt. Now E equal to here minus N into d phi is change in magnetic flux, right? Change in magnetic flux is final magnetic flux minus initial magnetic flux, whole divided by change in time dt, that is 0.2 second. Now E equal to minus N into phi 2. Phi 2 is 0, right? When you completely remove the coil from the magnetic field region, so what happens? There will be no magnetic flux. So 0 minus phi 1, that is magnetic flux through the coil, right? So that will be B into A. B into A. Okay, it is BA cos theta. Okay, theta is angle between magnetic field vector and area vector. Magnetic field vector and area vector both are in the same direction, so it is BA cos 0 degree. Cos 0 degree is 1, so it is just BA divided by 0.2, right? So induced EMF E equal to here NBA divided by 0.2. Now E equal to N is 80, B is, what is the value of B? 1 Weber per meter square into A. A is here 0.01 meter square, right? That is 10 to the power minus 2. Okay. Now solve this, you will get 0.8 volt. Okay. So the correct option is A. Next question, question number 6. The current flowing through an inductance coil of self-inductance 6 millihenry at different time instants is as shown. So this is the given graph. Okay, I versus t graph is given. Okay, the EMF induced between t equal to 20 second and t equal to 40 second is nearly. Okay, so here induced EMF E equal to L into di by dt, right? How we got this formula? We got this formula from this equation, right? L into I equal to N into phi, isn't it? So now differentiate both sides with respect to t, you will get this equation. Okay, so here what is di by dt? The slope of this graph, right? And L is self-inductance. Now E equal to self-inductance, L is 6 into 10 to the power minus 3 Henry, right? 6 millihenry into change in current. What is the change in current? Change in current is 4 minus 3. 4 minus 3 is, so this will be 4 minus 3, right? Or you can say 3 minus 4, right? Final is 3, initial is 4, right? So 3 minus 4. So if it is 3 minus 4, then this will be minus L into di by dt. Okay, so it will be 3 minus 4 divided by 40 minus 20, that is 20 only, right? So now solve this, you will get 3 into 10 to the power minus 4 volt. So the correct option is B. Okay, next question, question number 7. A rod of length 2 meters slides with a speed of 5 meters per second on a rectangular conducting frame as shown in the figure. Okay, this is the given figure. So this is the rod. Length of the rod is 2 meters. Okay, so it is moving towards left with velocity v. There exists a uniform magnetic field of 0.04 Tesla perpendicular to the plane of the figure. If the resistance of the rod is 3 ohm, the current through the rod is. Okay, so when the rod moves towards left, what happens? Here the area decreases, right? Isn't it? This area decreases. So if area decreases, that is magnetic flux through this area will also be decreases, right? If magnetic flux decreases with the time, what happens? Induced EMF produced in this rod, right? In such a way that it opposes the decreasing magnetic flux, isn't it? So the induced current will be produced in this rod, right? If induced EMF is produced in this rod, then current will also be produced. Induced current will also be produced in this rod, right? So what is the induced current? Induced current is equal to induced EMF divided by resistance of the rod R, right? So we need to find induced EMF of this rod. So we know the motional EMF, right? So what is the induced EMF of the rod when it is moving with velocity v? So it is B into V into L divided by R. Now I equal to, here what is the value of B? That is magnetic field. Magnetic field is 0.04 Tesla, right? So that is 4 into 10 to the power minus 2 into V, right? What is the value of V? V is 5 meter per second. 5 into L. L is 2 meter divided by R. R is 3 ohm. Now solve this. Okay, here you will get so 5 into 2 is 10, right? So 10 into 10 to the power minus 2 is 10 to the power minus 1, right? So 4 divided by 3 into 4 divided by 3 into 10 to the power minus 1, right? 10 to the power minus 1 ampere. So now solve this, you will get I equal to 133 milliampere. So the correct option is D. Okay, 133 milliampere. Next question, question number 8. The current in a coil of inductance 0.2 Henry changes from 5 ampere to 2 ampere in 0.5 second. The magnitude of the average induced EMF in the coil is. Okay, so the magnitude of the average induced EMF in the coil E equal to L into delta I divided by delta T, right? So this is the average induced EMF in the coil. Okay, so at a particular instant, induced EMF in the coil is L into di by dt. Okay, so this is the at a particular instant, at a particular instant. This is the average induced EMF, right? Average induced EMF. Okay, yeah. So now E is equal to self-inductance of the coil is 0.2 delta I, that is change in current. Change in current is 3 ampere divided by delta T. Delta T is 0.5, right? Now E equal to 0.6 by 0.5. Now E equal to 1.2 volt. So the correct option is D. Okay. Yeah. Next question. Question number 9. Consider the situation given in figure. The wire AB is slid on the fixed rails with a constant velocity. So this is the wire, okay, AB. So it moves towards a left direction. Okay, it moves towards left. Okay. So with constant velocity V. If the wire AB is replaced by the semicircular wire, okay, if it is replaced by semicircular wire, so like this, okay, semicircular wire A, P. The magnitude of the induced current will be, that is, what is the magnitude of induced current produced in this coil or induced EMF produced in the coil, right? Okay, think about it, pause and think about it here. Simple one, right? So magnitude of the induced EMF or induced current produced in this coil, induced current produced in this wire is same, right? Isn't it? It is same. It moves with the same velocity, right? It moves with the same velocity. So magnitude of the induced EMF or induced current produced in the coil is V only, isn't it? So the correct option is D, remains same. Okay. Yeah. Next question. Question number 10. A jet plane having a wingspan of 25 meter is traveling horizontally towards east with the speed of 3600 km per hour. Okay. So yeah, this is the plane. Okay. So the wingspan, the length of the wingspan is 25 meter. So it is traveling horizontally towards east with a speed of V equal to 3600 km per hour, right? So that is 3600 kilometer, that is 10 to the power 3 per hour in seconds. So it will be 3600 only. 3600 and 3600 will get cancelled. So it will be 10 to the power 3 meter per second. Okay. If Earth's magnetic field at the location is 4 into 10 to the power minus 4 Tesla, right? And the angle of dip is 30 degree. Then the potential difference between the ends of the wing, okay, at a particular location, Earth's magnetic field is 4 into 10 to the power minus 4 Tesla, right? Isn't it? So what we need to find here, we need to find vertical component of the Earth's magnetic field, right? Vertical component of the Earth's magnetic field. So what is the vertical component of the Earth's magnetic field? So vertical component of the Earth's magnetic field is B into sine theta, right? Theta is angle of dip, isn't it? So induced EMF E, that is potential difference between the wings, is induced EMF, right? Induced EMF E equal to B into V into L sine theta. So B sine theta is vertical component of the Earth's magnetic field. Now E equal to B is 4 into 10 to the power minus 4, V is 10 to the power 3, L is 25, sine theta is sine 30 degree, that is 1 by 2. So here 2 2s are 4, right? 25 2s are 50, right? Solve this, E equal to, you will get 5 volt. So the correct option is B. Okay. Yeah. Next question. Question number 11. The magnetic flux linked with the coil varies as phi equal to 3t square plus 4t plus 9. The magnitude of the EMF induced at t equal to 2 seconds is, okay, EMF induced E equal to n into d phi by dt, n equal to 1, right? The number of turns is 1. Now E equal to d by dt of, here the magnetic flux changing with the time t, right? Isn't it? So phi is 3t square plus 4t. So E equal to, what is the differentiation of 3t square? 6t. What is the differentiation of 4t? Plus 4, right? So at time t equal to 2 seconds, we need to find induced EMF E, right? Induced EMF produced in the coil. So E equal to, here t equal to 2, so 6 into 2 is 12. 12 plus 4 is 16. So it will be 16 volt. So the correct option is B. Okay. Yeah. Next question. Question number 12. A bar magnet is allowed to fall vertically through a copper coil placed in a horizontal plane. The magnet falls with a net acceleration. Okay, whether it is equal to G, 0, lesser than G, greater than G, right? Okay, so when the bar magnet falls through a circular coil, what happens when it is falling or when it is entering this circular coil? The magnetic flux through the circular coil increases, right? So the magnetic flux through circular coil increases, isn't it? Magnetic flux through coil increases, right? So if magnetic flux through coil increases with the time, what happens? Induced EMF will be produced in this coil, right? In such a way that it opposes the increase in magnetic flux, isn't it? Increase in magnetic flux, right? So that is, it opposes the motion of this bar magnet, right? It opposes the motion of the bar magnet. So here induced EMF will be produced, right? So it opposes the motion of the bar magnet, motion of the bar magnet, right? So the bar magnet falls with a net acceleration. Bar magnet falls with a net acceleration G lesser than G, right? Lesser than G. Lesser than G, isn't it? So the correct option is C. Okay. Yeah. Next question. Question number 13. The working of a magnetic braking of train is based on. So it is based on eddy current only. Okay. Eddy current. How eddy current produces? Due to the change in magnetic flux, right? Due to the change in magnetic flux, eddy current produces, right? So it produces in the opposite direction, right? It is the direction of the current is in opposite, right? Isn't it? Not alternating current or pulsating current. So it is due to the eddy current. Okay. So the correct option is B. Next question. Okay. So if you want to know working of a magnetic field, working of magnetic braking, okay, in a train. So in Google you can see, okay, in Google you can see the working of a magnetic braking of a train. Okay. So just go through the magnetic braking. Okay. So then you will get to know what is the principle and how it works. Okay. Yeah. If you have a time, otherwise don't go through all these things. Okay. Yeah. Question number 14. A jet plane of wingspan 20 meter, that is L equal to 20 meter, is traveling towards west at a speed of 400 meter per second. Okay, L is given, right? And the speed of the jet plane is also given, right? V. If the Earth's total magnetic field is 4 into 10 to the power minus 4 Tesla, right? Earth's total magnetic field is 4 into 10 to the power minus 4 Tesla, B, right? And the dip angle is 30 degree. At that place, okay, dip angle is 30 degree at that place. The voltage difference developed across the ends of the wing is, okay, so this is the wing, right? This is the wing. So it is traveling towards west. Okay, wing is traveling towards west. Not wing, this is the plane of the wing. Okay, here this is the jet plane of wing, right? So it is traveling towards west, isn't it? with a speed 400 meter per second, right? The length of this wing is 20 meter, right? So the magnetic field, the Earth's magnetic field is 4 into 10 to the power minus 4 Tesla, right? And the dip angle is 30 degree, isn't it? So what is the vertical component of the Earth's magnetic field? It's B sin theta. Vertical component of the Earth's magnetic field is B sin theta, right? So induced EMF produced in this wing, right, that is equal to E, which is equal to V into L B sin theta. V into L B sin theta, right? So the induced EMF produced in this wing means we are finding the potential difference across this wing, right? Isn't it? Or potential difference at the ends, isn't it? So E equal to V. V is 400 into L. L is 20 into B sin theta. B is 4 into 10 to the power minus 4 into sin theta. Sin theta is 1 by 2. So 2 2s are 4, and then E equal to, solve this, you will get 0.8 volt. So the correct option is D. Okay. Yeah. Next question. Question number 15. A long solenoid with 40 turns per centimeter carries a current of 1 ampere. The magnetic energy stored per unit volume is. So the magnetic energy stored per unit volume, U equal to half B square divided by mu naught. What is B? B is magnetic field inside the solenoid, okay, or magnetic field due to the solenoid, and mu naught is magnetic permeability. Now magnetic field due to the solenoid or magnetic field inside the solenoid, B equal to mu naught N into I. Everybody knows mu naught. Mu naught is absolute permeability. N is number of turns per unit length. I is current in the solenoid, right? Now B square is mu naught square N square I, right? Now energy stored, magnetic energy stored per unit volume, U equal to, here, mu naught square N square I square divided by 2 mu naught. Mu naught will get cancelled, right? So U equal to, mu naught is 4 pi into 10 to the power minus 7 into N square is 40 square, right? 40, okay, it is turns per centimeter, right? That is N equal to 40 turns per centimeter, that is 40 into 10 to the power 2, okay. 40 into 10 to the power 2 is 4000, so 4000 squared into I square is 1 divided by 2, 2 2s are 4, right? U equal to, here 4000 square is 4 square, so 4 square is 16, right? Isn't it? So 4000 is 4 into 10 to the power 3, right? 4 into 10 to the power 3 squared is 16 into 10 to the power 6, right? So 16 into 2 into pi into 10 to the power minus 7 into 10 to the power 6 divided by 2. Anyway, 2 got cancelled, right? Yeah. Isn't it? Now U equal to, it is 32 pi into 10 to the power minus 1, right? That is 3.2 pi. 3.2 pi. What is the SI unit? Here SI unit is joule per meter cube. Joule per meter cube. So it is joule per meter cube. So the correct option is A. Okay. Next question. Question number 16. A wheel with 10 spokes, each of length L meter, rotated with the uniform angular velocity in a plane normal to the magnetic field B. The EMF induced between the axle and the rim of the wheel is. Okay. So here, this is the wheel, right? So this is the spokes, right? So it will rotate with the angular velocity omega, right? So induced EMF between the axle and the rim of the wheel, right? So it is, everybody knows, so it's half B omega square into L, right? Isn't it? Half B omega into L square. Sorry, half B omega into L square, not omega square into L, omega into L square. Induced EMF E is equal to half B omega into L square. Okay. So if you don't know how we got this formula, go through the NCERT electromagnetic induction chapter. Okay. So in that they have given the derivation. Okay. Just go through the derivation. Once go through the derivation. So the correct option is B. Okay. Next question. Question number 17. An aircraft with a wingspan of 40 meters flies with a speed of 1080 km per hour in the eastwards direction at a constant altitude in the northern hemisphere. When the vertical component of the Earth's magnetic field is 1.75 into 10 to the power minus 5 Tesla, then the EMF developed between the tips of the wings. Okay, so EMF developed between the tips of the wings E equal to BV, that is vertical component of the Earth's magnetic field, into V into L. So E equal to BV, that is 1.75 into 10 to the power minus 5 Tesla into V. V is 1080 km per hour, that is 1080 into 10 to the power 3 divided by 3600 into L. L is 40 meter. Now solve this, you will get E equal to 0.27 volt. So the correct option is D. Okay. Yeah. Next question. Question number 18. Two coils have a mutual inductance of 0.005 Henry, that is 5 millihenry. The current changes in the first coil according to the equation I equal to Im sin omega t, where Im equal to 10 ampere and omega equal to 10 pi radian per second. The maximum value of the EMF induced in voltage in the second coil is. Okay, so here we need to find the maximum value of the induced EMF, okay, produced in the second coil, right? Induced EMF, the maximum value of the induced EMF produced in the second coil, E equal to M into di by dt, right? How we got this equation? We know the relationship between mutual inductance M, current in the coil I, and N into phi, that is magnetic flux, right? Here M into I equal to N into phi, right? M into I equal to N into phi. So M into di by dt is equal to N into d phi by dt, right? N into d phi by dt is induced EMF E, right? So E equal to M into di by dt, isn't it? Now here E equal to M into di by dt, that is d by dt of Im into sin omega t, Im into sin omega t. Now induced EMF E equal to M into Im into omega cos omega t. Differentiation of sin omega t is cos omega t, omega cos omega t, right? So induced EMF E equal to here Im omega is Em, that is maximum induced EMF produced in the coil, Em into cos omega t. So Em is equal to M Im omega. So Em equal to M is 5 into 10 to the power minus 3 into Im is 10 into omega is 100 pi. So solve this, okay. So you will get Em equal to 5 pi volt. So the correct option is A. Okay. Next question. Question number 19. A solenoid inductance 2 Henry carries a current of 1 ampere. What is the magnetic energy stored in the solenoid? Okay, so magnetic energy stored in the solenoid, U is equal to half Li square, right? Magnetic energy stored in the solenoid, U equal to half into L into I square, right? A solenoid of inductance is given. So this is the value of L, right? And I is 1 ampere, right? And U is magnetic energy stored in the solenoid. So U equal to half L, that is 2 into I square, that is 1 square. 2 will get cancelled. U equal to 1 joule. So the correct option is D. Okay. Yeah, next question. Question number 20. A rod PQ is connected to the capacitor of plates. The rod is placed in a magnetic field B directed downward, perpendicular to the plane of the paper. So this is the magnetic field, right? It is directed downward, perpendicular to the plane of the paper. If the rod is pulled out of the magnetic field with the velocity v as shown in the figure, okay, so option A says plate M will be positively charged. Okay, let's see. Here the rod is moving towards right, isn't it? So here the area is decreasing, right? Area is decreasing. If area is decreasing, magnetic flux through this area will also decreases, right? Magnetic flux through this area will also decreases. Now what happens? Induced EMF will be produced in this rod, right? Isn't it? Why it produces? Why induced EMF is produced? Because it opposes the decreasing magnetic flux, right? It opposes the decreasing magnetic flux. Magnetic flux changing with the time t, right? It opposes the decreasing magnetic flux. Okay. So what is the direction of the induced EMF, right? So this is the direction of the V, right? This is the direction of the V, right? Magnetic flux is into the plane, right? Hold your fingers, the tip of the fingers, or direct your tip of the fingers along the V, right? Then curl your fingers towards B, right? So the direction of the magnetic induced EMF is from P to Q, right? Direction of the induced EMF from P to Q, right? Isn't it? P to Q. This is so now we can represent this rod like this, right? Q and P. Now P is connected to the positive terminal, Q is connected to the negative terminal. So plate M will be positively charged, plate N will be negatively charged. So option A is the correct answer. Plate M will be positively charged, isn't it? Next question. Question number 21. A and B are two metallic rings placed at opposite sides of an infinitely long straight conducting wire as shown in the figure. If current in the wire is slowly decreased, the direction of the induced current will be. Okay, so the current in this wire slowly decreased. Di by dt is decreasing, right? Isn't it? So what is the induced current produced in this coil? Whether it is clockwise or anti-clockwise, we need to figure it out, right? Okay. So what is the magnetic field at point B? Here the magnetic field at point B is into the plane, right? It is into the plane and it is decreasing, right? To oppose the decreasing magnetic field, induced current will be produced in the coil, right? Isn't it? So in such a way that it opposes the decreasing magnetic field, right? Isn't it? So in which direction induced induced current has to be produced? Induced current has to be produced in clockwise direction, right? Apply right hand thumb rule. Here the magnetic field produced by the induced current should be into the plane, right? So it has to be clockwise direction, right? Induced current has to be in clockwise direction. Similarly, apply Lenz's law. Here I have applied Lenz's law, right? Similarly, apply Lenz's law for point A. So what is the magnetic field in point A? So it is outward from the plane, right? So magnetic field is outward from the plane and it is decreasing, isn't it? So to oppose the decrease in magnetic field, induced current will be produced in this coil, right? So in which direction? In anti-clockwise direction, isn't it? In anti-clockwise direction, right? So in coil A, the induced current will be in clockwise direction, right? Here anti-clockwise direction. Sorry, it will be in anti-clockwise direction. Sorry. Here this will be in anti-clockwise direction. Here this will be in clockwise direction. Okay. So A will be in anti-clockwise direction. Okay. In A, induced current will be in anti-clockwise direction. In B, induced current will be in clockwise direction. So the correct option is B. Okay. Yeah. Next question. Question number 22. A vertical conducting ring of radius r falls vertically with a speed v in a horizontal uniform magnetic field B, which is perpendicular to the plane of the ring. Which of the following statement is correct? A and B are at the same potential. This is absolutely wrong, right? Why it is wrong? See here, this is here this ring is falling down with velocity v, right? Isn't it? Isn't it? Okay. Okay, so here, so let's bend this ring in a straight line, right? So this is point A and B. So this will be a straight line, right? Or straight wire falling down, right? And the magnetic field is uniform, isn't it? So induced EMF will be produced, or the potential difference will be there between A and B, right? Between A and B, the potential difference will be there, right? Isn't it? So A and B are not at the same potential, okay? So option A is wrong. Option B, C and D are at the same potential. This is correct, right? C and D are at the same potential. Okay, let's take these two. C and D are endpoints, okay? So now bend the wire into this as a straight wire, okay? Bend it. Okay, now it is a straight wire. C and D, it is falling down like this with velocity v, right? Is there any induced EMF produced? No, right? Isn't it? C and D, is there any potential difference? No, right? Potential at C is same as potential at D, isn't it? So option B is the correct answer. Okay. Okay, next question number 23. Three identical coils A, B and C. Three identical coils A, B and C carrying currents are placed coaxially with their planes parallel to one another. Okay, so these are the three coaxial ring, okay, current carrying ring, okay. Their planes are parallel to one another. A and C carry current as shown, okay. So A carries the current, so which is okay, from this point of view, the direction of the current is clockwise, okay, in A. In C, it is anti-clockwise from this point of view, okay, from this point of view, okay, from here, the direction of the current changes, okay, yeah. B is kept fixed while A and C both are moved toward B with the same speed. Initially, B is equally separated from A and C. The direction of the induced current in the coil B is. Okay, so here, due to the current carrying loop A and C, the magnetic field will be produced, right? Isn't it? Or magnetic flux will be produced. So it passes through the B, right? So what is the magnetic field through B? The direction of the magnetic field is like this, right? It will be like this through B, isn't it? So what is the direction of the magnetic field through B due to C? So it will be like this, right? Isn't it? Right? It will be like this. So what is the net magnetic flux through B? The net magnetic flux through B is 0, right? Isn't it? Magnetic flux due to A will be cancelled by magnetic flux due to C. Both are in opposite directions. So net magnetic flux through B will be 0, right? Isn't it? So the direction of the induced current in the coil B is 0. That's it. So option C is the correct answer. Okay. Next question. Question number 24. An electron moves on a straight line path y dash as shown in the figure. A coil is kept on the right. A coil is kept on the right such that y dash is in the plane of the coil at the instant when the electron gets closest to the coil. Neglect self-induction of the coil. Electromagnetic induction. Okay. Electromagnetic induction. Option A says the current in the coil flows clockwise. Okay, let's see. Here, as electron gets closest to the coil, right? So we know that the direction of the current is opposite to the direction of the motion of the electron, right? So what is the direction of the current? The direction of the current is like this, right? It is opposite to the direction of the motion of the electron, right? So now what is the magnetic field or direction of the magnetic field which is passing through this coil. The direction of the magnetic field passing through the coil is outward from the plane, right? Is outward from the plane, isn't it? As electron moves towards point O, right? As electron moves towards point O or O dash. So which is closest to the coil, right? Isn't it? As electron moves towards O dash, what happens? The current will be increases, right? The current increases, isn't it? If current increases, the magnetic flux through this coil will also be increases, right? According to Lenz's law, if magnetic flux changes with the time, okay, then induced EMF will be produced in the coil, right? If magnetic flux through the coil changes with the time, induced EMF will be produced, right? To oppose that, induced EMF will be produced. So here induced EMF or induced current will be produced in the coil to oppose this increase in magnetic flux, right? So in which direction? Here the magnetic field due to the induced current has to be in opposite direction, right? This way, that is into the plane, right? So in which direction induced current will be produced? Induced current will be produced in clockwise direction, right? Isn't it? Induced EMF will be produced in clockwise direction, or the current will be produced in clockwise direction. Induced current will be produced in clockwise direction. Clockwise direction. Okay, so the correct option is A. Next question. Question number 25. Okay, figure shows three regions of magnetic field, each of area A, and in each region magnitude of magnetic field decreases at a constant rate alpha. If E vector is the induced electric field, then the value of line integral E dot dr along the given loop is, okay, so here these are the three regions, right? 1, 2 and 3. Area is A, right? Here the magnitude of the magnetic field decreases with the constant rate alpha, that is minus dB by dt is equal to alpha, right? So due to that, induced electric field will be produced, right? So then the value of line integral E dot dr along the given loop, right? So what is the direction of the loop here? The direction of the loop is anti-clockwise, right? So if it is anti-clockwise, then take area vector which is outward from the plane as positive, then into the plane is negative, right? So the net flux through this loop phi will be equal to here minus BA. See, area vector is outward from the plane. In these two regions, magnetic field is into the plane. So both are in opposite direction. So theta will be 180 degree. So BA cos 180 degrees is minus BA. Minus BA plus BA. So phi is equal to minus BA, right? So now differentiate phi with respect to t. Now d phi by dt is equal to minus d by dt of b into a, right? Minus d by dt of d by dt of b into a, isn't it? So now area is not changing, right? So this will be a into minus dB by dt, right? Minus dB by dt, isn't it? Minus dB by dt is alpha. Now here the line integral, okay, E dot dr vector is equal to a into alpha. So option A is the correct answer. Okay. Next question, question number 26. Two identical conductors P and Q are placed on two frictionless rails R and S in a uniform magnetic field directed into the plane. Here the magnetic field is directed into the plane, okay. So these are the two wires P and Q, okay. It is placed on a rail R and S, frictionless rail, okay. If P moved in the direction shown in the figure, so this is the wire P, right? So it moves towards left with velocity v or with speed v, shown in the figure with the constant speed, then rod Q, option A says, will be attracted toward P. Okay, let's see. When P moves towards left, what happens? Here the area will increases, right? Here the area will increases, isn't it? So if area increases, what happens? The magnetic flux through this area will increase, right? If area increases, then magnetic flux will also be increases, right? Here area increases with the time, that is magnetic flux increases with the time, isn't it? The magnetic flux here, magnetic flux changes with the time, isn't it? Magnetic flux phi changes or increases, right? It is increasing, changes with time, right? Magnetic flux increases with the time, right? So according to Lenz's law, to oppose this increase in magnetic flux, what happens? Induced current will be produced, right? Isn't it? In this wire, right? In both wire P and wire Q, isn't it? So here, to oppose this increase in magnetic flux, what will happen? Induced current will be produced in Q, right? The wire Q. So the wire Q will also move towards P, or wire Q will be attracted toward P. Okay, why? Because the area will decrease, right? Isn't it? Area will decrease, so it is opposing the increase in magnetic flux, right? So wire Q will also move toward P. So option A is the correct answer. Okay, so it will be repelled away from P, wrong, right? So if Q repelled away from P, what happens? The area will increase, right? That is magnetic flux through this area will increase, isn't it? Right? So it is wrong, right? According to Lenz's law, it is wrong, isn't it? So option B is wrong. Option C will remain stationary, again wrong. Option C may be repelled away, no, wrong. Or attracted toward P, wrong, right? Question number 27. A square loop of side 1 meter and resistance 1 ohm, here L equal to 1 meter, okay, R equal to 1 ohm, is placed in a magnetic field of 0.5 Tesla. If the plane of the loop is perpendicular to the direction of the magnetic field, the magnetic flux in Weber through the loop is, here this is the loop, okay, square loop, and this is the direction of the magnetic field, okay, this is the direction of the magnetic field, and this is also the direction of the area vector, right? Area vector is perpendicular to the plane of the square loop, right? Isn't it? So the magnetic flux through this square loop is phi equal to B dot A, right? So what is the direction of the B and A? It's same, right? Parallel, right? Isn't it? So the direction is in upward, right? The direction is upward and both are in same direction, right? So the magnetic flux phi is equal to BA cos theta, right? Theta is angle between magnetic field vector and area vector. So it is 0 degree, right? Because both are parallel to each other, right? So 0 degree, phi equal to B into A. Cos 0 degree is 1, right? Phi equal to B into A. Now phi equal to B is 0.5 Tesla, right? And area is L into L square, that is 1 into 1 meter. That is 1 meter squared. So phi equal to 0.5 Weber. So the correct option is B. Okay. Simple and easy question. They will ask these kind of questions. Okay. Yeah. Question number 28. In figure, there is a conducting ring having resistance R placed in the plane of the paper in a uniform magnetic field B. If the ring is rotating in the plane of paper about an axis passing through point O and perpendicular to the plane of the paper with constant angular speed omega, okay, so this is omega in clockwise direction, then so this is the given figure, right? Here the line which is passing through O, right? So the ring is rotating about this axis, isn't it? This axis with angular velocity omega, right? Okay, so let's check each option. Point O will be at higher potential than A. Wrong, right? How? So do one thing, join these two lines, that is join these 2 points, that is point O and point A, right, by one rod. Okay, by one rod join A and O. Okay, so now this rod is rotating with angular velocity omega, right, about its axis, isn't it? The rod is rotating on its axis with angular velocity omega, right, isn't it? So the potential difference, that is VA and VO, will be 0, right? The potential difference will be 0, right, isn't it? Isn't it? The potential difference will be 0, right? So if potential difference is 0, then the induced current will also be 0, that is there is no induced EMF, right? So the induced current will also be 0. So here there is no current in this loop, right? There is no current in this loop. So point O will be at higher potential than A. This is wrong, right? This is wrong. Option B, the potential of point B and C will be different. Wrong. It is same, right? It is same, isn't it? Potential and B, here the potential at point B and C is same, isn't it? Do one thing, again join these 2 points by one rod, right? So it's like the rod is rotating, right? The rod is rotating like this, isn't it? The rod is rotating like this, omega, isn't it? With angular velocity omega, right? So if rod is rotating about the axis OA, then there will be an induced EMF, right? Induced EMF in this rod, isn't it? So the potential at C and B both are same, isn't it? The potential at B is same as potential at C. So option B is wrong. Option C, the current in the ring will be 0, correct, right? Option D, the current in the ring will be wrong. This one is wrong, right? So the correct option is C. Yeah. Next question, question number 29. A 0.1 meter long conductor carrying a current of 50 ampere is perpendicular to magnetic field of 1.25 millitesla. The mechanical power to move the conductor with a speed of 1 meter per second is. Okay, so the mechanical power to move the conductor with a speed of 1 meter per second, right? So P equal to induced EMF produced in the coil, E into I, right? E into I, isn't it? So current carrying here the conductor carrying a current 50 ampere, isn't it? I equal to 50 ampere. You need to find induced EMF. Now P equal to, how to find induced EMF, right? So this conductor is moving, right? Moving in a magnetic field, right? So P equal to B into V into L, right? P equal to B into V into L into I, right? So now we need to find P. So P equal to, what is B? Magnetic field, right? Magnetic field is 1.25 millitesla. So 1.25 into 10 to the power minus 3 into V. V is here 1 meter per second into L. L is 0.1 meter into I. I is 50 ampere. Okay. Then P equal to here 50 into 0.1 is 5. 5 into 1.25 is 6.25, right? So 6.25 into 10 to the power minus 3 watt, right? Or 6.25 milliwatt, right? So option B is the correct answer. Okay. Yeah. The next one and the last one. A conducting ring of radius r, so this is the conducting ring of radius r, is rolling without slipping with a constant angular velocity omega. Okay, so this conducting rod is rolling without slipping at with a constant angular velocity omega. If the magnetic field strength is B, here the magnetic field strength is B and it is into the plane, right? The direction of the magnetic field is into the plane and is directed into the page, then in EMF induced across PQ. Here EMF induced across PQ we need to find, right? This one, right? So now do one thing, here join the PQ, the point PQ by rod, okay? So this is the rod, okay, red color one. Here R and R, right? So apply Pythagoras theorem. Now apply Pythagoras theorem. Now this distance, that is the distance between P and Q, is root of 2 into R, right? Root of 2 into R. Now this rod is rotating, right? This rod is rotating with the angular velocity omega, isn't it? So now we know that here when rod is rotating in a uniform magnetic field, the induced EMF in this rod E equal to B omega L square divided by 2, right? B omega L square divided by 2. L square divided by 2. L is root 2R, right? So E equal to B omega root 2R squared divided by 2. Now E equal to here root 2R whole square is 2R square, right? 2 will get cancelled, so it is just B omega R square. So the correct answer is A. Okay, correct option is A. Okay, thank you so much for watching this video. If you love this video, please like and share. Okay, so if you want to watch more such videos, please subscribe. Thank you.